Okay, so as promised, let's go ahead. All our work thus far has been in quad 1. Everything seemed to go fine. So what about if we move quadrants, right? Because we know that we can rotate past 90 degrees and 180 and 270. And basically it all comes down to drawing that right triangle again. So let's go ahead. Here's a situation. Again, I have an angle theta. It's rotated into the quad 2. And so I'm going to pick any ordered pair that lies on its terminal side. Again, remember from the last video, it doesn't matter which ordered pair I use, right? We have a similar triangle argument. And looking for a right triangle, right? Basically, we've got that guy right there, right? We're always going to take a parallel line to the y-axis towards the x-axis. And then what I have, right, this distance right here would be the x-coordinate. This distance right here would still be the y-coordinate, and this distance right here would still be r. So I can still create, right, a right triangle situation in quad 1, which basically means we have the following. Now that I have this right triangle, right, we know that r squared should equal x squared plus y squared, because that's the Pythagorean theorem. Of course, that gives us what we already know in quad 2, that r is x squared plus y squared. And because we have this right triangle, right, we now have the ratios going for, as a matter of fact, we always have those ratios, right? It shouldn't impact the ratios at all. So what's the ratio for the angles for theta? Well, it's the y-coordinate over the r-coordinate. What's the ratio for cosine? Well, it's the x-coordinate over the r. What's the ratio for tangent? Well, you take that angle and it's still y over x. I keep doing that, right? And of course, then they're flips, right? The cosecant of that angle is r over y, right? The secant of that angle is still going to be r over x. The cotangent of that angle is still going to be x over y. So our definition still works, right? Everything's still in order if we're in quad 2. We're still going to rotate from the initial side along the x-axis. We're going to stop somewhere in the quad 2. We can pick any ordered pair I want, and each one of those is going to create a right triangle situation, right? Which gives us the Pythagorean theorem, so we can redefine, or well, not we're redefining, we're verifying it again that r is still the square root of x squared plus y squared, and then this shouldn't impact the ratios because it's really depending on your x, y, and r values. And again, that's why I call this the x and y r definition. So it's just that my x, y is over in quad 2, so it shouldn't change the definition at all. And our angle, can still rotate over there. And if you're following along, I guess quad 3 shouldn't be a big deal, right? Because again, for this particular situation, right, where's the right triangle at? So I can draw my little picture and see all this. Well, again, we're always going to put a line parallel to the y-axis and going to the x-axis. So now there's my little right triangle. This side is the x, basically the x coordinate. This is the y, and there's your r yet again. So again, we have this verified that r is the square root of x squared plus y squared, because that's what the Pythagorean theorem basically tells us for that little right triangle in quad 3. And of course, now that I have an ordered pair, or I've always had an ordered pair on that, what is the sine of that angle? Well, it's still going to be the y-coordinate over that r-coordinate that we created. What's the cosine of that angle? Well, it's still going to be the x-coordinate over that r. And what's the tangent of that angle? Well, it's still going to be the y-coordinate over the x-coordinate, what I have. And of course, we have the reciprocals. The cosecant is still going to be the r over the y. The secant is still going to be the r over the x. And the cotangent is still going to be the x over the y. So we can still build our r. R still makes sense. So therefore, our ratio for sine makes sense, our ratio for cosine of the angle makes sense, and our ratio for tangent always makes sense because it doesn't depend on r, right? It's just y and x. So you have an x and y coordinate, you can always find the tangent. So hopefully you can see that this definition still works in quad 3. And of course, if you're really following the conversation, you can see how this is easily going to work in quad 4, right? Because now what we have, right, again, we're going to draw a line that's parallel to the y-axis going towards the x-axis. There's my right triangle. This side represents the x length, this side represents the y, and in this little right triangle we have my r. All right, and so again, because of the Pythagorean theorem, r is still x squared plus y squared. And because I can now find that r in quad 4, that means my definitions for sines and cosines and secants and cosecants still exist. Of course, we always had tangents, so I'm not going to bother to rewrite them. They're still there. So this now means that our trig functions, using the definitions, using the ratios, you give me an angle, I take the sine of that angle, I get that ratio. This ratio works for any quad 1, 2, 3, or 4. You give me an angle, the cosine of that angle, right, is always the ratio x over r, no matter which quadrant that I'm in. You give me an angle, and I take the tangent of that angle, it always gives me the ratio y over x. Okay, and so that again shows that our definition is well grounded, right, and it works for all angles, because after that point, right, we're coterminal, so we can go on forever and ever and ever and keep talking about sines and cosines and tangents. One last thing again I want to address, make sure you're aware of the fact that we are breaking away from the old idea, right, of using a function name like f and an input of x and an output of y. Right? Again, we're no longer calling input x, we're calling our input theta. We're no longer calling our function f, we're giving it one of our function names, sine, cosine, tangent. You have 6 choices, right? And then the output of that, well, depends on which ratio we're talking about. Sine is always the y coordinate over the r, right? And the cosine of that angle is always going to be the x coordinate over the r. And the tangent is always going to be the y over x. All right, and of course then we have the other 3, which I'll go with that, without name. And so the output is no longer just y, right? The output is some ratio of y, x, y, and r. And hence that's again why I call this your x, y, r definition of our trig functions, because every angle, right, has a terminal side that contains a point x comma y. I've showed you that we can always find r by using this formula, and so the 3 things I need to define my trig functions are all there. I have an x coordinate, I have a y coordinate, and I have an r value. And so we can always define our trig functions at any location. All right, and so there's your groundwork. Hopefully it's beginning to make sense. Let's start doing some homework problems where we can really just start putting it in action. All right, and so we'll move to a different part of the module and we'll go from there. And again, as usual, if you have questions, please contact me, email